In this video, I would like to say more on the Lie algebra elements that generate finite rotations through the matrix exponential. So I will show you that this matrix exponential indeed can describe a generic rotation around an axis which is given by the direction of a vector n. So it's a unit vector n. I will show you with MATLAB. In further videos, I will also give you some more intuition, some more mathematical intuition, because this can also be derived more directly. But here, I want to give you some important intuition behind this, which is different from the intuition that you will get from further videos. So this can be tackled from different perspectives, but in my opinion, it's important to understand visually what's going to happen here. So in particular, let's assume that we are in 3 dimensions and we have some direction n, so it's a unit vector, and then we have a vector v. So at first I'm going to sketch something and I'm going to find some simple formulas, and after that we are going to do some implementation in MATLAB, skipping the actual calculations, nasty calculations if you want. So there is nothing nasty, but in this case I want to focus on actually the intuition without hardcore calculation with matrices and so on. So still I will use some vector notation in this video. Anyway, here you have this vector v, and we have to rotate this vector v around the vector n by some angle. So how do we define the angle? In particular, if you think about it, the projection of the vector v on n, which is this one here, is going to be unaffected, whereas the component that's perpendicular to the vector n is the one that we are going to rotate, right? So the angle will define the rotation of this perpendicular component. So the component along n can also be written like this. So we have to take the dot product between v and n to find the projection along n, and then the direction is given by n. So we can also write it like this. On the other hand, we can also obtain the perpendicular component by subtracting the parallel component. So this is just simple algebra. We can also write it like this. So this one here is parallel to the vector n, whereas this one here is perpendicular to the vector n. That's quite understandable, right? And another way to construct a component that's perpendicular to n, for example, is by taking the cross product between the two vectors n and v. By doing this, you get something that's perpendicular to n due to the properties of the cross product. For example, the mod squared of v can be written as the square of the component along n plus the component perpendicular to n. Because if you remember, v dot n can also be written as the cosine of alpha times v, if we define the angle alpha to be the angle between the vector n and v, which is different from the angle of rotation that we are going to use later. So we have to rotate v around n, and that's a different angle. So alpha is a fixed angle. It's an angle between n and v. Whereas the cross product, the mode of the cross product is the sine of this angle times v. So when you do this algebra, it's easy to see that you get cosine squared plus sine squared multiplied by v squared. So you can see that here you just get 1. So this formula is correct. So you can see that in this formula we have n cross v. We are using n cross v here and v dot n or n dot v. Now, I can also introduce a matrix to express a cross product in 3 dimensions. In particular, a cross product can also be written as a matrix that I'm going to call K times the vector V, so apply to the vector V. And considering the notation that we used in the previous video, in particular this one here, Ln equal to nx Lx plus ny Ly plus nz Lz, this K is actually L, the vector L dot product n, which I also denoted as Ln. So in this video, I'm going to use the notation K. And you can check that if you take L dot n, and remember that the three matrices Lx, Ly, Lz are given by these expressions, and the vector n is given by a vector of components nx, ny, and z. You can put those matrices together and you get the matrix K here. I'm not going to write the components, but you can check, you can show that that's equal to the cross product between the vector n and v. So that's just simple algebra. If you know how to take a cross product, you can do that quite easily, and that's the result that you have to obtain. Now, if we focus on the two perpendicular components that I have written, in particular, I have written n cross v, which can also be written as kv, we can show that this is perpendicular also to v minus v dot n, n. And this one here can be written as minus k squared v. And why is that? Well, kv, we know that's equal to n cross v, even if I have not directly proved it. And if we apply another k, we get k squared v, and therefore that's equal to n cross v. So it can be written like this. And if you use the properties of cross products, that can also be written as the dot product between this vector and this vector, so n dot v multiplied by this vector n, minus the dot product between these two, which is n squared, and that n squared is equal to 1 because it has unit norm, times the third vector here, which is v. So I have basically proved this formula here, and now we can see quite easily that this vector is perpendicular to this vector here. That's due to the fact that k squared v can be written as k applied to kv. But when we apply k, we create a cross product with the vector n. So it can also be written like this, in this form. And when we write such a quantity, such a vector, it means that the resulting vector will be perpendicular to n, right? And also to this one here. So k squared v, which is this one as well, will be perpendicular to both kv and also n. So we can write, we can think that the situation is something like this. Here we have the vector n that's coming out of the screen. Then we can sketch the vector v minus v dot n, which is equal to minus k squared v. And then we have another vector that's perpendicular to the other two. We can think that this is on the same plane as this one. So we have a plane here, and then n would be perpendicular to the plane. And this one here is also a right angle between this vector and this other one, which is n cross v, or if you want kv. So I know that it can be nasty. It can be, I mean, a little frustrating the first time that you have to do these calculations because you have to think about it. You have to know all the properties, and it might take some time to adjust to that. But so here I want to try to be concise without wasting too much time on this kind of stuff. I think that it's important for the intuition, but we are not really going to use it in other videos. What I want to show you is that the exponential form of rotations can also be directly related to another way to write the same thing by using different types of matrices, a different type of notation. But let's move on here. So I will write v prime, the rotated vector. So this will be the vector after the rotation by some angle theta. And that's the rotation around, let me repeat it, the vector n. So we want to rotate v around n by an angle theta. And the angle theta is an angle defined on the plane of the perpendicular projection. So v prime can be written as, we know that we are not going to rotate the part parallel to n. So this part here is parallel to n, and it will remain unchanged. Then we have another part that's perpendicular to that, and in particular, the part that we need to rotate is basically this one here, because before the rotation, the vector v can be thought of as v dot n plus, of course, you can rewrite the subsequent part as v minus v dot n. So we need to rotate this part here, which is this one. So v prime will be this one unchanged plus this one rotated. And I'm going to call that, so this will be the rotated part, and this will be the angle theta. I will call that zeta. But you can call it whatever you want. So it's this rotated vector. I mean, it's this one rotated by an angle theta. So we need to write zeta. And zeta will be equal to the mode of the previous this vector here, which is unaffected by the rotation. So the rotation will only change the orientation, but it will not change the magnitude. So the magnitude is still equal to k squared v, plus or minus. So the magnitude, of course, will be unaffected by the sign, because when we take the magnitude of a vector is equal to the magnitude of minus the vector itself. So that's easy. And then we need to find the direction of zeta with respect to this vector and this vector here, which we will use as some kind of basis to express the orientation of zeta. We can do that. So in particular, we can write the cosine of theta along this direction. So we can write that direction as minus k squared v divided by the mode of that, right? And then we have plus the sine of theta, and then we have the other component. So the other, I mean, this sine of theta will be along this direction here. So that's given by n cross v divided by the mode of n cross v, like this. Now, another simple thing to see is that the mode of k squared v is equal to this mode here. And that's because we can write it as n cross kv. But this is also equal to n cross v. And the angle between this vector and this vector here is 90 degrees. The fact that these two are perpendicular can be seen very easily if we take the dot product between these two vectors. So n cross v dot product n is of course equal to 0. Why? Because this vector is perpendicular to the cross product between these two. By definition, because v cross n or n cross v will generate a vector that's perpendicular to n, so that's 0. And therefore, the mode of that can be written as the mode of this vector, which is 1, times the mode of this vector, which is n cross v mode, times the sign between the two vectors, this vector here and this vector here, but the angle is 90 degrees, and therefore that's equal to 1. So we have proven that this mode is equal to this one. So we can use that result to simplify basically this with this and also with this. So we can rewrite v prime as, by substituting in place of zeta this expression, we can rewrite it as this one, which I'm also going to rewrite by considering this equation. So from this equation you can write v dot n equal to v plus k squared v. So we have v plus k squared v. Then we get minus k squared v times the cosine of theta, so we can rewrite it as 1 minus cosine theta, plus, and then we are left with n cross v, which we can write as k v times the sine of theta. All in all, we can rewrite it as v prime equal to the identity matrix multiplying this v, so I will write v in here, plus k squared times 1 minus the cosine of theta, plus k sine theta. And this is the important matrix that performs that rotation around the axis n, that we can denote as r sub n of theta, if you want. So it's a rotation with an angle defined as theta on a plane that's perpendicular to the axis of rotation, and the axis of rotation is n, is characterized by the unit vector n. And this is also called Rodrigues matrix, and this formula here is known as Rodrigues formula, which is also the title, of course, of this lecture, if you want. And this Rodrigues matrix is important because it is related to the matrix exponential that I have written here. So it could be derived by doing the algebra, the calculations. It can be done. I will not do it here, but I will do something similar in subsequent videos as well, in later lectures, in later sections, if you are interested, but that's not the point here. I have prepared a quick script which defines the unit vector. So here I define the unit norm of the vector. I define the vector n with the three components. Then I define k, and k can be written in this form. I mentioned it earlier that k is this cross product. So the matrix k will be written in terms of the components of n. And I mentioned also that it can be written in this form, so L dot n. So you can also obtain it by considering these three matrices and doing the dot product with a vector of these three matrices. So you take the first matrix and you multiply it by nx, plus you take this matrix and you multiply it by ny, plus you take this matrix and you multiply it by nz, and you can show that you get exactly the same thing. So you get you get the matrix K. You can obtain it either from here or from basically, as I said, L dot n. And so once you do that, so I have defined it like this. I have also here, I'm calculating a matrix given by e to the theta k, and I'm doing it in MATLAB here. And then I calculate a Rodrigues formula like this. And finally, I do a difference. I take the difference between the matrix Rx and the Rodrigues matrix. And once we do the calculation and we take the subtraction, we can see that we obtain a zero matrix like this, which simply means that the two are equivalent. So this matrix here, the matrix resulting from this exponentiation, will be exactly equal to the Rodrigues matrix, which is related to a rotation around an axis. So that's also the intuition that I wanted to give to you to understand more deeply this important aspect of rotations.